to making solution for problem number 14 moving 10. The problem says that when we let's start again, please. When we connect two nodes, one heavy and one light, with a string and put it over a bar, in some circumstances, a lighter rod can stop the heavier one from falling down. So our crucial task for this phenomenon are going to be to find cause why the lighter rod can stop the heavier one, find the initial range of parameters when this phenomenon occurs, also investigate at which height the heavier rod will stop for different initial values. Next, to see our theoretical prediction and our aperture, we have two loads, one light, one heavy, and also gravity force going and down. They are connected with the string over a bar, so there are two tension forces, T1 and T2. Also, we have dynamic friction force between rod and rope, so we have friction between rope and rod. In this case, we have Newton's equation that talk about movement of both loads, lighter and heavier. If we write also, we have two more equations. This is the Keston equation that connects tension forces T1 and T2, and this is the exponential correlation. So this is the key point why the lighter load can stop the heavier one. Also, in our experiment, we use non-elastic string, so we can use an equation that talks about constant length of the string. To simplify our theoretical model, we will separate into two parts. We have first part of the motion, when both loads moving, lighter and vertically just falling vertically downwards. Next, when we solve our Newton's equation and write it on x and y axis, we got our equations that talk about the movement of the lighter rod. Now, when we pass to the second part of the motion starts when the heavier rod stops. The lighter rod will continue to move and sweep around the rod. Because of this little change, the heavier rod stopped moving, we have little bit changed our equations. If we took our final equations 5, 6, and 7, we want to make, based on them, our theoretical prediction and simulation. To make theoretical prediction and simulation, we need to know all initial parameters. All of the initial parameters could be measured except friction coefficient. So first task are going to be to find friction coefficient. To find friction coefficient between rod and rope, we make simple aperture, same like at machine. We connect two rods, two bolts, one heavy and one light, with a rope over a rope. In that case, there are going to be dynamic friction coefficient between rope and rope. So we record this phenomenon and find the time that takes for the heavier rod to fall down. We put it in our equation and we find that the friction coefficient for our two strings is 0.18 and 0.24. Next, based on these equations, and now when we have our theoretical model and friction coefficient, we make simulation. This is our simulation that connects light load and heavy load, also the string. When we look at the trajectory of the lighter load, we can see it's nice and everything, and it is just to the model. But to see does the simulation works, we need to check it with the experimental results. To do that, we need some aperture. So we use easy aperture, lighter load, heavier load, rod, and camera. Camera was put it directly in the X of the rod. Every measurement was repeated 5 times, and we recorded this phenomenon and analyzed trajectories. And it's important to notice what's the successful measurement. The successful measurement is considered if the loads haven't hit each other and the rope does not slip off the rope. Now, when we look at our simulation and over it put our experimental results, we can see that we have really good matching with theoretical and experimental results. But our simulation is not perfect, and it has some parts that we does not calculate, like air resistance. But we can prove it that it does not have big influence. This we said that the air resistance is air resistance coefficient times velocity. We put the lighter rod on the rope and release it to oscillate. In that case, we have how does the amplitude change, and we record this phenomenon and do just the amplitude points. So we find that the air resistance coefficient is this number. Also, when we analyze our video footages of the trajectory of the light rod, we find that the maximum velocity that the light rod has is 0.80 meter per second. So when we calculate drag force and gravity force, we can conclude that the drag force is much smaller than gravity force. So furthermore, we don't. So in our simulation, we don't have drag force because of this. And there's one little thing. Our simulation is just 2D model, but in reality, we don't have 2D problem because if we release rods in 2D plane, they will hit each other. So we need some small angle alpha that will to avoid that collide of the rods. To see is there any influence on trajectory for a small angle alpha, this is the azimuthal angle, we record trajectories for 3, 5, and 7 degrees. And we conclude that there's no such big differences in trajectory for those angles. So we didn't conclude in simulation, so our simulation is just 2D model. To see which parameters are really important, our equations 5, 6, and 7, we transfer to the dimensionless equations. From here, we can see there's only 4 important parameters. This is the mass ratio, length to the radius ratio, friction coefficient, and initial values for some parameters. So for those parameters, we are going to show you our first experiment. In our first experiment, we try to find areas when this phenomenon occurs and when this phenomenon does not occur. We did for different mass ratios and also length to radius ratio for 3 different angles. We can see that there is optimal mass ratio that's around 7 for every degrees for every initial angle. And also we can put this optimal mass is shrinking down when we have a smaller release angle. Also from here we can put there's some lowest value from for L to R ratio. Next one, in our second experiment, we varied the length of the string. This is the length of from rod to carry rod, from rod to collider rod, and this small part that's on rod. And we measure the height at which the carry rod will stop. From this graph, we can see that when we increase the length of the whole string, the height at which the carry rod will stop will increase. This is also predicted with our theoretical prediction, and on this graph we have really good matching with theory. Next, we varied mass ratio. This is the ratio one to another mass, and we did that for 2 different masses of the lighter rod. From this graph, we can put something very important. This is that our phenomenon does not influence masses, just their ratio, and also we predicted that with our theoretical model. So in here, on this graph, we also have good matching with our theoretical model. Next one, we vary the starting height of the heavy rod or starting position. We do that for our 2 strings with friction coefficient 0.18 and 0.24. We can see that when we increase the starting position of the heavy rod, it will stop at bigger height. Also, we can see that there is small differences between 2 friction coefficients, and it is intuitive and somehow logic that the rod with bigger friction coefficient will stop the heavy rod quicker. In our 5th experiment, we varied something very interesting. This is the release angle, and we varied from 30 until 90 degrees. And we did that for 3 different radius of the rod. And we also this time measured the height at which the heavy rod will stop. From this graph, we can conclude that when we increase the release angle, the height at which heavy rod will stop decreases. Also, we can conclude that when we increase the radius of the rod, the height at which the heavy rod will stop increases. In this case, we have the good match with the theoretical predictions, so we are very happy with our simulation. To conclude everything, our task said that we should connect 2 rods, one heavy, one light, with a string over the road, and see when it can keep the heavy one from falling. So first of all, we give you a reason, in our opinion, why the heavier, lighter road can stop the heavier one. This is kept in equation in my opinion. Also, we make our simulation that completely represent experimental results, and we also have really good matching with experimental and theoretical results. Our first experiment was that we changed initial values of parameters to find the range when this phenomenon occurs. We find that the optimal mass ratio is around 7, and we also find just four important parameters. For our second, third, and fourth, and fifth experiment, we conclude that when the height at which heavy roads stop will increase, when length of the string increases, mass ratio increases, starting height of the heavy load increases, release angle decreases, friction coefficient decreases, radius of the cross decreases. Also, we find something interesting, and this is also predicted with our simulation model. This is that our phenomenon does not influence masses, just their ratio. And finally, we have pretty good matching with theory in all experiments. Thank you very much.
So, dear opponent, could you please name the qualitative explanation why light load can sweep around the rod in a few words?
Why it can sweep?
Why it can sweep? What's the reason?
Because it has some initial speed in that direction, so it can just sweep around.
Okay, got it. Did you have some releasing mechanism or you put your light load on loose hands?
I don't have mechanism, but I have controlling environment. I have some probe that
Was human factor controlled or not?
no human factor.
And did you compare the dynamics of the system? For example, how so you had trajectory comparison, but did you check that it compares in the time? For example, for example, height of light load, heavy load with time or something like it on the trajectory.
We compare height at which heavy load will stop.
So
for every measurement.
No dynamic of the process checking here. Okay, got it.
I disagree.
I'll explain to you later. So if you have, for example, so it's like our rod, our heavy load, and our light load. If we fix length of the light load to the rod, friction coefficient, initial angle, and mass relationship, and only change the distance till heavy load to the rod, will something change? If only this will be changed, all these parameters will be changed.
Just the final height of the road. Differences will be the same, just final height.
And what was the shape of your light load? So when you compare the air friction, what was the shape of?
It was spherical, like a ball.
I got it. And for heavy load?
Also spherical.
Did you see the how light load collides the rod or no?
No experiment. Colliding between two rods.
When light load sweeps around and after it
hits the bar or the rod. Yes, I see that this phenomenon.
And how do you see? Isn't this important this phenomenon?
Yes, but our simulation does not cover that part. Our simulation stops when the light load hits the rod.
about the light load and stop of heavy load. But in the presentation, we didn't see the observation of phenomenon. That's such a pity. And we didn't hear the qualitative explanation why can heavy load sweeps around and heavy load stops. One clarifying question I asked about it. I was asked that light load can sweep around because it has some initial speed, but I don't agree with this because, for example, we can have like this rod. We have string for some and just release from some angle and release the light load. It will just oscillate like mathematical pendulum without sweeping. So this qualitative explanation isn't enough for this phenomenon. We'll discuss it later. So what was done with this report? First of all, that was written the mathematical model based on second Newton's law. I totally agree with it. It's this mathematical model was okay. After it was comparing for experiment, but it wasn't checked if light load if heavy load can go down, stop, and after it go down again, because it can be at important this phenomenon. So it is not so strong point, but still comparison was good, but not on time. So we seen how the trajectory comparison, the height velocity down comparison, but we didn't see if this theory can predict the motion of system in time. Because so if trajectory is okay, but it can be, but we didn't see, for example, how the time for heavy load stops can change. So for example, the trajectory can be higher, it can be fast in a few times, and it can be big mistake. Also talk about the friction that isn't so important this phenomenon. And the really cool thing I've seen in this report is taking into account the three-dimensional of the surface of the phenomenon. Because it's what's obvious is that in two-dimensional phenomenon can be observed. And it was proved that for writing equation it isn't so important, but for qualitative equation it's a very strong point. After it was found boundary conditions in which we can see phenomenon, but only experimentally. So it could be better if it could be predicted by theory. So the main strong point of this report is that we have theories that can predict the experiment, but not on time. That the three-dimensional phenomenon was taken into account. That there were some parameters in which we can observe phenomena, but not predicted theoretically or experimentally. And that we have the method how he measured the efficient coefficient. I agree with it because it's a problem. It's important to measure efficient coefficient correction in order to have good agreement theory. But if you think about points to improve, there was no qualitative explanation of the phenomenon at all, and it isn't so good. It wasn't predicted. It wasn't explained how he understood that heavy load stops because it wasn't reflected in the record. And for this moment, there are 2 points how he can do it, and he could make a mistake in this one. After it, we didn't see any demonstration of experiment. It's such a pity because there are really important things that we could see on this exhalation, and no proof of strings that inextensible and wafers that he used in his theory. So if talking about task fulfillment, what can we see? That yes, it was done, the loads were connected because we have some experimental data, but we didn't see the observation, so we have to do it that it was done. It was poor qualitative explanation of the phenomenon, but it was theoretical model that could predict such dependencies as heavy load goes down and the trajectory. But it isn't enough, in my opinion. So problem was partially solved. Now I want to go to discussion. Okay. So I think that first of all we have to talk about the qualitative explanation of the phenomenon because as I said in my speech, if you said that the reason is just velocity. So let's say we have such string, such load, and just release it. It also has some initial speed, but it won't sweep. So it isn't for us.
Yes, but we misunderstand each other. We have camera with big road and with small white road. And this is some when time is not 0, the camera will stop in this time. Okay? And we have tension force, we have gravity force, and we have some initial velocity in this direction. So this initial velocity will make the right road.
But how can he get this initial velocity to sweep?
Okay.
What's the mechanism of increasing this velocity?
This is the type of first part of the motion, and So
And it goes
something,
down.
something when you so then add up these two forces, we get something like this.
Yes, of
So
course.
it's a negative force that can roll, slip around the roll.
But don't you see that, for example, energy transfer between these two loads can be important? So that this, so do you think that it can be explained like that? This load gets some energy by the equal to this one because it goes down, because this load goes down, and by the tension force, energy goes to this.
We also have some losses in this experiment by friction coefficient.
Yes, of course. So friction decreases energy transfer. But
Yes, yes.
so you agree with it? The extent of energy transfer.
Energy of the light rod will increase because it's on like smaller
Yeah.
height, but the energy will increase because it's velocity.
So to this moment, we've discussed with the reporter that the energy transfer can be of explanation for the sweeping of the light load. Now let's, I think, move to the next stage of the system, of the motion of the system after the heavy load stops. I think it's not. Thank you. So let's make a picture. So we have a rod,
Okay.
and light load stop, and so
Everyone. Or
heavy one, yeah, its velocity is equal to 0, so it doesn't move. And light load is somewhere there, like the like. What can happen after it? So in your mathematical model, you say that after it, light load just sweeps and that's all. But I don't think that it is all that can happen.
there are going to be three different phenomena that could occur. in this. First of all, the successful measurement that occurred. This is when light rod sweep around, stop, and this is correct.
Yes,
The
I agree.
parallel
This
velocity.
can happen.
But there's some. This is the second. That when if the light rod have so big velocity, and it hit the road with big velocity, in some cases and some angles, it can go backwards
And what will happen?
and slip go backwards and slip around.
And what will happen with heavy load in this
If
case?
this velocity and going backward is big, heavy load can fall down. But
I agree with you.
if the velocity and this
So
going
depending
backward,
on the velocity, you want to say that depending on the velocity and the point light load
Yes.
sweeps
Like
the rod,
this.
it can even fly away and not be observed.
yes, but this phenomenon is hard to simulate, this light between rod and
Yeah, in this
and
case,
light. So we
I don't think that it's so hard. Just, but it isn't the main part of the report, so it's okay that you didn't investigate it. And what's the third part? What's the third motion?
Light rod can just make just stop right here because air drag or friction coefficient.
I don't think that it's more about so
Because
so in your experience you really saw that it's just stopped. Oh no! Did you see in your experience that it really stopped?
not
Oh, no. Or it-
starting to fall down. And
Yeah,
I think every rod will
and
fall
what's
down.
yes, and let's now draw the picture and try to explain why is it happening and why it is important. So you have potential force there, for some value there, and when it goes down, what happens with tension force? So we have some tension force there, and some tension force there. What was so heavy load doesn't move at all.
Picture, but I think you
So it is the rod, it is the light load, and it is the light load, and heavy load doesn't move; it stops.
okay.
So where tension force will be bigger? In which point?
When the velocity of the light rod is
Yeah, I
increased,
totally
this is
agree
the
with you.
down position.
And now let's see. You have non-slipping condition, yeah?
Not superposition.
Not slipping condition for Ayler's formula for friction. So let's see what happens. You say that tension force acting heavy load is tension force acting light load, and exponential is something there.
Yes.
And let's see what happens. Let's see what happens in this case. This tension force decreases. So this tension force, it increased. And so, because of it, not all, from a different point, let's say, heavy load, light load stops the heavy one at this point. So this formula doesn't work still because still doesn't work.
Yes, we need to separate dynamic and static.
Yes, understand. But what I want to say is that in this point it can go back again.
Yes,
Yes,
so
so-
compositors pitch.
So I mean that heavy load can stop after it go down again without striking the rod, just because tension force in this point decreases.
I didn't see this
You
phenomenon.
didn't And did you try, for example, menstruation about 4?
About what? Yes, I want to show you.
It's very okay. I believe that you use it, but it's strange that you didn't see. Yes. So okay, till this moment we've discussed with the opponent what happens after the heavy load stops. That it can be strike between the rod and the light load, and the light load can go up, and after heavy load will fall again because tension force will decrease. So next question I'd like to talk with you about is that just so you have assumption that you said that your string is extensible and weightless.
Yes.
So let's first of all talk about what happens if our string is not inextensible.
Okay.
So let's talk about that it's just some deformations. What will change in the system?
First of all, we could not make our simulation on base of these
Yeah,
situations.
of course, but just qualitatively, what happens qualitatively?
Distance between two loads can increases because our
Let me draw the trajectory of light load. First of all, it was there, and so what is the trajectory of light load? Is
if there is one elastic string, it's going something like this.
and if we have elastic string,
Okay, now say
Yeah.
that it should go a little bit downwards to make a little bit bigger trajectory because it can
but
extend.
do you think that there can be maybe some oscillation of it to this position?
I think there could be some oscillations, but I didn't try to do this experiment in elastic
I
string.
got it. But one more question about the elastic string. If our string will be very elastic, so just like is it like resinka, just made of. So where is it deformate? Like is even by hands?
Okay.
Do you believe that this will be? Because in my opinion, in this case, phenomenon can be absolutely different. So if you have very easy deformated string, after we release light load, it will go like it because tension because the heavy load goes down. And what's the value of tension force at the moment when heavy load just what's the value of tension force at the moment when heavy load just began going down?
I could not measure tension force when the heavy load stops.
But I disagree with you. It is because it's equal to 0. So see, heavy load just go down. First moment, it's just free falling because we released this one without some initial parameters. And so see, in this because the tension force is equal to 0, in this point is also equal to 0, and so because the string is very elastic and it had so big deformation, it just flies like it.
Yes,
And it can bring the phenomenon to absolutely new level because not inaccessibility of the string change phenomenon very hard. For example, like this one, or just oscillating the system.
I do believe it is so elastic string. This phenomenon will not occur.
Yeah, there are also phenomena that
I think
Can-
this
that can
be
be-
some other phenomenon. I don't know which, because this is not our task. We should.
So in my opinion, change the functions of the string is important. So during the discussion with the opponent, we've talked about the qualitative explanation and got the agreement that energy transfer between the loads can explain this phenomenon very well. But of course there are some energy losses because of the friction between rods in the string. After it, we've talked about the motion of the system after the heavy load stops. That there are three possible modes. That heavy load can go down and stop without anything. That it can go down and after it light load will strike the rod and heavy load will go down again and the system and so no more drops off the top. And after it the third mode is that light load can sweep around, go to some higher position and heavy load will go down and stop again. So these three modes. After we talk about the role of the string, that if you have not an extensibility string, there are possible some, first of all, radius of the spiral will be increased, but also there will some oscillation between the elastic velocity is very high. Yeah. Thank you for your attention.
show me the slide? What is the, why are these deviation between the theory and experiments?
This deviation is pretty small.
There are some error bars, but the theory don't correspond with the plotted data.
Okay, this is the smallest mesh ratio when this phenomenon occurs. So this is the hardest thing to do because it's some cases successful, some cases unsuccessful measurement. So in this case, when it's so small mesh ratio, we have bigger errors.
Okay.
Like I showed on graph on experiment number 1.
Opponent, your opinion on
In my opinion, can be the errors, for example, can be included in a measurement of friction coefficient. So to include the errors, it will be more, it will be better agreement, and errors bars can.
Okay, thank you.
And also it can be not enough repeatance of which is there.
Reporter, please, have you done some simulations for boundary conditions? You shown us some graphs for boundary conditions of
The particular boundary conditions.
Have you done some simulations from theory? Okay. Now I'd like to ask you, how do you release the load?
Okay, I had three things in my experiment to release light road perfectly. I have one string that shows us 90 degrees. Also, we have one wooden plane under it, and we place the light rod on it. When the time to release light rod, we just move the wooden plane to us, and the light rod will start going down.
It's good for you, opponent? Is it good?
In my opinion, I think that this phenomenon is better to create some random mechanism. For example, add a string with some additional. Let me draw it.
Fast
Yeah,
answer,
of course.
please.
This rod and string and this light load. And we just add it with some additional string to, for example, table, and
Okay.
with fire break it. So we
Yeah,
don't
I
have this
understand.
case
Thank you.
effect.
Opponent, please, why is for you important the time diagram the reporter don't show us?
For example, it's because it's as you could know with the problem, it's Ivan Ilgin's solution in his website. It can predict the theory, but can't predict the dynamics. Because in this problem, it's important to predict the dynamics.
I agree with you. Is it important for you the time diagram in your work?
I show some diagrams, but we should. Our task is when the light rod can stop the carrier one. So we show you these experiments, and also we make simulation, and this is dynamic in time.
Thank you. And last, fast question: can we use a Kaplan equation for dynamic friction? Yes or no, please?
Just yes or no. Yes.
Good afternoon, ladies and gentlemen. Once again, My name is Tomáš Wolf and I'd like to review this task, problems 14 looping pendulum. First of all, I'd like to somehow summarize the reporter's presentation. He presented some qualitative explanation, but from the discussion, I must agree with the opponent that is caused by the transfer of the energies, not the initial spin. Then he draws some equations based on the Newton's equation and Kapstan equation and show us his theoretical description. Also, he shown us the comparison between theory and experiments. I think it's fit quite well, but as you can see exactly in this graph, there are some deviations, and I'm not sure if everything in this experiment was done properly. He also measured the friction and drag force, these coefficients he put to his equation for some improvement in the theory. He also explored some relevant parameters as mass ratio, what I appreciate. But what we really missed were the time diagrams of the difference of the different difference in the axis of the rotation, for example, x. What is changing in the time? We think it's a part of the crucial part of the presentation, what should be presented. Once again, to the reporter's prose. He makes some qualitative explanation, but it's not so good. I think we can discuss if it's good or no. Then some theoretical description, lots of experiments, and he taken into account the 3D, the third dimensions. To the cons, as I have spoken about, the deviations and the missed time diagrams. Some preliminary questions the opponent was asking about why it can rotate. As the reporter said, it was from his side the initial spin. We don't agree. We don't agree with the reporter. We agree with the opponent. Is the transfer of the energy. Then he asked about the time diagrams, what we missed. Both with the opponent. Also, we agree with the opponent. And he also asked about the shape of the light load. I think it's not so relevant question, but I think the spherical is the good option for the reporter's measurement. To the opponent's pros and cons, he pointed out the missing explanation and the other relevant points that we missed also in the reporter's presentation, as time diagrams, deviation, and so on. And he has deep knowledge about this problem, as he shown us in the discussion. But we think that he could talk more about what the reporter has done than some hypothetical questions. The discussion, some main points, for example, about the explanation of the rotation I have spoken about. We agree with the opponent that is a transferred energy and is the important mechanism in this task. Then he was asking about what happened after the stop. The reporter was talking about 3 possibilities. We think it's a very good question in this task. Then he also discussed the Kapstan equation. I think there should be some changes in order to use for dynamic friction. And to the end, they discussed the deformation of the string. I think that could be the reason why we can see this deviation of the releasing the load and this deviation caused by the elasticity of the string. That's all from me, and I thank you for your attention.
Okay, it's right, I know. Yeah, I should summarize the presentation, and let's start with discussion. In discussions, we talk. The biggest part of the discussion was talk about elastic and non-elastic string. So I think this is not so relevant. This is hypothetical questions, and I think we should talk a little bit more about our experiments and our results. Also, we talk about some initial values, initial parameters, transfer of energy. Should we talk with energy explanation or velocity explanation? Also, we talk should we use Kapstan equation? Should we not use a Kapstan equation? And also we talk a little bit about releasing mechanism. So this is good point. Maybe there was a little human error to some, but I think no. Just to summarize our simulation, our presentation, I think I show in a diagram when I have matching the theoretical and experimental results over the time. This is the graph, and also from our simulation, we think we can took velocity, angular velocity, everything for light and heavy load. But our task is when the heavy load can keep the light from the falling down. Also, from our presentation, we conclude when the height at which the heavy load will stop increases, when decreases. We also varied 4 important parameters, and we find this is the 4 important parameters. Also, we made our theoretical model. We explained why it can be 2D model, why we cannot, why we could skip air drag. Also, we have good matching with theoretical. So I can conclude that I think we feel the task complete.
I have the question for the reviewer. You said that the capstan cannot be used for the kinematic friction. So there's some modification has to be made. Can you suggest that?
I think there should be some changes because the capstan equation it's not.
What changed?
What change? I think we can ask my colleague that was this idea was changed.
Actually, we would have to include some acceleration of the string. However, I would not use that. I would do it like another way, such as because dynamic and static friction is kind of different.
Okay.
Yeah.
So the opponent, you agree with the reviewer?
If it talks how to operate capstan equation, we could take account that string isn't weightless and it has some acceleration. So these two changes we have to do to this equation.
The reporter?
I can say if we have matching with theoretical and simulation, we use this capstan equation, so we can use this equation because we have matching. This is my conclude, and I think we can use capstan equation for dynamic and static friction.
Thank you.
Just a quick follow-up. So did you do the distinction between dynamic and static friction in your simulations? Because you were mentioning just one value before.
Did I measure the static friction?
So did you measure the two friction coefficients, and did you insert both of them in the simulations? So did you
No, I just measured dynamic friction, but they're, I think, pretty same. There's some small fluctuation between dynamic and static friction.
You mentioned something about boundary conditions in the question.
Yes, the reporter shown us some graphs, the diagrams of the mass ratio on the x-axis and the y-ratio, something on the y, I'm not sure what. And you can see the green, yes, this one. I was asking if he I think it's from the experiments, isn't it?
Yes.
Yes, and I was asking about some predictions from the theory. If we can this boundaries when is the phenomenon successful and not can predict from the
boundaries.
yes, this was I was asking.
Can I ask you this question? Can I
Yes,
give answer?
I just wanted to know which.
So can you go to the slide where you use your main equation for do the calculation?
Yeah. I don't know which one. This one.
Okay, just leave it there for a minute. Do you want?
Question for a moment. Since you have talked about the electricity of the string, can you suggest to the reporter in which part of his theory it should be changed in order to consider the electricity of the string?
So he, in one of his first question about certain point mistaken, of course, he writes inaccessibility of the string, so this component should be chosen for using, for example, some rules for deformation. And so in this case, length of the string will be constant, it will depend on the tension forces on both ends of the string. So it should be changed in this case.
For the reporter, can you point out the term for the friction between the rope and the rod?
Yeah, this is this part. We only have this friction coefficient, and we need to go back to see where does it came from. from first equation. This is that part. Capstan equation is source.
So the opponent, you agree with the reporter that he used the exponential term from the capstan for the
Yes,
friction
used-
between the road
Yes,
and the
used
rod.
Eros formula for friction between rod and the spring.
The reviewer,
I agree with them.
Maybe because that's what's about this masses to stop. You discuss about this massive whether they stop and maybe for presenter first and the other. Why do these masses stop? What happens when they stop? Because I somehow missed this.
Tension force acting on the heavy rod became greater than gravity force pulling them down. So this is the, let's say, easiest explanation. But why this tension force became so big? This is because capstan equation and type of motion.
It's friction between the rod and the spring, so because of it, tension force acting heavy load is much heavier than light load. It increases this angle of contact, and so because of this, the tension force can become bigger than gravity one. So because of friction.
sure.
So I think you are ready for. For the report, it's 67766. For the opponent. It's 67576. For the review, it's 55585. Let's start with the review.
Sorry, in the review, I actually really liked your also questions and the review of the report and opposition because you, as the first thing we pointed out that the opponent didn't even touch the presentation more or less, and you asked about the errors, which was the thing that was in my mind the whole discussion. So basically, I identified below your point, and I thought that you, the time management was good, and that also your prioritization was very good. So you just was talking about you were talking about the relevant things and clearly. So and then I maybe was not very happy about the boundary condition because I had for the jury, and then about the dynamic capstone equation because this was something that you disagreed with both of them, and then you, at least to me, you didn't really justify what the problem was or your colleague. So that's maybe a bit of a downside, but otherwise I really like that this was a good.
Thank you. Yes.
Sorry for what we did.
You're ready. So actually, I do yes, and also had these two issues. These two questions where actually one was clear out and it was understood what you asked about the issues, and we just had we're unfortunate. The boundary condition is already used in many other conflicts, and we gave the judges a wrong picture of the what it has nothing to do prevent the boundaries of these regimes which you can clear up so much. But for the dynamic friction part, there is some points. Because I think we should have been able to justify this technical statement. And also, so let's continue, maybe somebody else has to say.
Maybe with the low score because I think you didn't summarize the reporter presentation, cover everything, and then also the review opposition. There's some point that you might need to add more.
Let's continue with the report.
I think it's not to use experiment to prove that those energy loss or air frictions are not even needed to be included in your experiment comparisons with the field ones. So it's a smart way to do the presentation. We can see that opponent have no way to judge his idea. So I think you really a smart on the presentation part.
I also like it.
Even though you got a lot of things not yet complete, I do think that it already have a good sign to show you have a good presenting skills. Talk about the lack of investigation about really talk about the phenomenon. It shouldn't be only one formations or one pattern you can see. You know how to use the phase diagram, not phase diagram. Actually, is to identify successful and accessible. You use the pattern to show success and success. You also can do about another observation that opponent have every time trying to write out that you just talk about one phenomenon, not others. You also have to influence.
It was also for me one of the main reasons why I subtracted your points, because you had only this most simple kind of mode in your presentation. Discussion, I think this came out quite well.
I like the theory. I think that there is a small error because I think you assume that the rope is always moving in one direction or the pole. So I think in the case when the rope moves in the other direction, you will have actually to make an exponential minus instead of plus. But that's a detail. And I think that in the presentation, I mean, one of the most surprising things, at least for me, in these problems is this exponential law, this Kepler's law around the pole. I know it's a it's the thing to use, but I think the justification for this, a more intuitive justification, was maybe surprising exponential dependence, because usually it's the area plays a role with friction, right? This should have been come out a bit more. But otherwise, I think it was good.
Six for me is like the same as I saw this problem before, and the team that did this problem did better job than your team. So, but you did answer the question with the opponent, okay? So to come out to be the same as another team because they cover more condition than you. And I think the interesting phenomenon is that when the mass heavy load coming down and then got pulling back again. Yeah. So that I think that's some interesting part in that dynamics of this process.
I don't remember what was the highest score. Maybe start with the lowest score and you can end off kind of. Okay.
Well, I decided to give a low score because I got 5, yeah. And so, because well, during the discussion you used all the time for discussion of the model. You didn't have time to discuss the experiments, the results. And another thing is that during your speech you promised to explain why this must stop. And finally during the discussion I just somehow missed that. I don't know, maybe that is what I missed that. So yeah.
That's really what's that.
Okay. Yeah, you have posed this interesting phenomenon in the discussion, and I come up with 5 of the 5 parts you have talked about. But during your discussion there, they're far away, you mess up everything. It's not clear if it supports your idea to convince the imposter. So you really got 8 or 9.
So I was enjoyed that you pointed out different rules. And maybe what I would have enjoyed is if you had done a bit more on the model as the model for the derivation for the differential equations that you had. If you had asked a bit more questions on that and how the Kapston law exactly goes into the differential equations. I would have enjoyed it, but otherwise it was. So then we come to the end of this round. Thank you very much. Really very interesting discussions and very fair contact.